9.2, we make a shift from just sequences and convergence into series and convergence. So if we have a series, the sum from n equals 1 to infinity of a sub n, the nth partial sum is given by adding up the first n terms. And if we have a sequence, s sub n, that's converging to s, so if we look at the sequence of partial sums, and that sequence of partial sums is converging to some number s, then our series to infinity will be converging. The limit s is also the sum of the series. And if that series of partial sums is diverging, if the sequence of the partial sums is diverging, then the series will be diverging also. So we start by looking at the sum from 1 to infinity of 1 over 2 to the n. And you may recognize this as a geometric series, but we're going to hold off on that idea just for the time being. And we're going to use this to explore this idea of the sequence of partial sums. So s sub 1, I guess we could expand this out. This is 1/2 plus 1/4 plus 1/8, and so on. This is an infinite series. The first partial sum would be 1/2. The second partial sum, 3/4. The third partial sum is 7/8. The fourth partial sum is 15 over 16, just adding up the first four terms. And if we look at the nth partial sum, we want to come up with some sort of an explicit rule to give us that nth partial sum. And what you may notice is that all of these terms, the numerator is 1 less than the denominator, and that denominator is always a power of 2. So what we now want to know is, what is the limit of this nth partial sum as n goes to infinity? And you should be able to see that this limit is equal to 1. We want to find the sum of this infinite series, 1 over n minus 1 over n plus 1. I'm going to do this similar way as before. I'm going to write out the series. So this becomes 1 minus 1/2 for the first term, plus 1/2 minus 1/3, plus 1/3 minus 1/4, plus so on and so on. S sub 1 would be 1/2. S sub 2, the second partial sum, is 2/3. S sub 3 is 3/4. And the nth partial sum, if we're looking at this sequence of partial sums, can be given by 1 minus 1 over n plus 1. And the limit of that as n goes to infinity, the second piece goes to 0, so this limit is equal to 1. And what this is this is an example of a telescoping series. In a telescoping series, when you expand it out, what you're going to end up having happen is all of these inside terms are going to cancel out, and you're left with the first term plus the limit of the last term. And if I go back to this previous problem, adding on a generic term at the end, notice that all of these inside terms are canceling out. The 1/4 will cancel with something, and this 1 over n will eventually cancel, and what we're left with is 1 minus that piece right there. So what this telescoping series test tells me is exactly what we just saw happen. Now we want to find the sum of this series, and we're going to do this in two ways. We're going to start by writing this sequence of partial sums. The first partial sum would be 2/3. I'm plugging in 1 for n. The second partial sum is equal to 4/5, because if I write this series out, we get 2/3 plus 2/15. I'll write out a couple more terms here, plus 2 over 35, plus so on and so on. The third partial sum is 6/7, and the nth partial sum can be found by taking 1 minus 1 over 2n plus 1. And since we have a term for that nth partial sum, we can look at the limit. What happens to that sum as n gets infinitely large? This is equal to 1. So the sum of the series is equal to 1. Now another way that we could have come up with this is by taking that fraction that we start with as our rule, and that can actually be decomposed into partial fractions. And what we get if we do partial fractions on this, the denominator is a difference of squares. We get 1 over 2n plus 1 minus 1 over 2n minus 1. And if I write this out, what I find is that this is equal to 1/3 minus 1 plus 1/5 minus 1/3 plus so on and so on, plus this generic term and then we can look at what's going on with these cancelings. I apologize, I can't read my handwriting. The 2n minus 1 fraction should be positive 1, and the 2n plus 1 should be negative. So that's just going to change all the signs inside of here. And what happens now is this negative 1/3 cancels with the positive 1/3. This negative 1/5 will cancel with the positive 1/5 in the next term. And the term before this will have a positive 1 over 2n plus 1, and that's going to cancel. And what I'm left with is a 1 plus limit as n goes to infinity of 1 over 2n minus 1. And since the limit of this last term is 0, my sum of the telescoping series is just 1. Now, hopefully we should remember that for a geometric series, if the absolute value of the common ratio is less than 1, then we have this property here. Sum from n equals 1 to infinity, a times r to the n minus 1, and I forgot the minus 1 in the notes there, but that's equal to a, the first term, divided by 1 minus r. And just for the sake of rigor, I am going to include a proof of this sum formula. So if r is equal to plus or minus 1, then what we have is an alternating series, and this will diverge. If r doesn't equal plus or minus 1, then the nth partial sum is equal to a plus a times r plus a times r squared plus so on and so on plus a times r to the n minus 1. And the common ratio times that nth partial sum gives me a times r plus ar squared plus so on and so on plus a times r to the n minus 1 times a times r to the n. And if I subtract these two equations, I'm left with s sub n minus r times s sub n equals a minus a times r to the n. And I can manipulate this a little bit to give me the equation s sub n equals a over 1 minus r times 1 minus r to the n. And this you might recognize as the formula for any geometric sum for the nth partial sum. But now I want to look at what happens as n gets really, really big. And one thing to note is that as n goes to infinity, r to the n will go to 0 if r is between 1 and 0. So the limit as n goes to infinity of s sub n is equal to this limit of a over 1 minus r, 1 minus r to the n, which would be equal to a over 1 minus r. But that's not the end of the proof. What we've shown now is that this will converge if r is between 0 and 1. But we have to now show that this doesn't work if r is bigger than 1. So let me clear some room here. And we're now going to make the statement if r is bigger than 1, then notice what happens to r to the n. R to the n goes to infinity as n goes to infinity. So the limit as n goes to infinity of 1 minus r to the n diverges. Thus does our sum rule. And the rest of this proof for negative r's would be along much the same lines. Now we're going to write a repeating decimal as a fraction. 0.08 repeating is equal to 8 over 100 plus 8 over 10,000 plus so on and so on. This is a geometric series with a common ratio being 1 over 100 and a first term being 8 over 100. So this sum is 8 over 100 minus 1 minus 1/100th, or 99 over 100. So 0.08 repeating can be written as 8 over 99. Now we want the sum of n equals 4 to infinity of 1 over 2 to the n. Now, if we had the sum from n equals 0 to infinity of 1/2 to the n, which is another form of 1 over 2 to the n, we could use this sum formula, where the first term is 1, and the sum is equal to 2. But that's not what the problem is. The problem here says the sum from 4 to infinity. What we can do is take this 2 and subtract the third partial sum. And notice that I need to start at 0 here to make my first term equal to 1. So when I find this third partial sum, I'm actually starting by plugging in n equals 0. So this sum is going to be 2 minus 1 plus 1/2 plus 1/4 plus 1/8, and that sum is 1/8. Another theorem for convergence, this is for the limit of the nth term of a convergent series. If the series converges, then the limit as n goes to infinity of that generic term will be 0. But the converse of that isn't true, necessarily. We can't say that if the limit of the last term goes to 0, then the series will converge. That statement does not work. It's true for this is true, but the converse, flipping these two statements around, that doesn't work. But what we can say is that if that limit as n goes to infinity isn't 0, then we know that the series will diverge. If the limit equals 0, it's inconclusive. We don't know if it converges or diverges. It might diverge, it might converge. We don't know. There's more work that we would need to do. But we can safely say that if that limit isn't 0, there's not a chance that it can converge. So Now we want to check to see if this converges or diverges. We have two sequences here, or two series. And what we can do is take the limit of the rule this limit of 2 to the n is equal to infinity, which is not equal to 0, so the series diverges. In the second example, the limit as n goes to infinity of 1 over n equals 0, so it might converge, it might diverge, we don't know. This is inconclusive. This test that we had, the nth test for divergence, is inconclusive. Since the limit equals 0, we don't know what's going on. So here are the problems that you should be working on out of 9.2.